Welcome to the Biocrates webinar on the Quantitative Metabolomics database, the QMDB, a novel database providing quantitative plasma concentration ranges in human individuals based on the standardized Biocrates MXP Quant 500 kit analysis. My name is Gordian Adam, and I am a senior scientist in the data interpretation team at Biocrates Life Sciences based in Innsbruck, Austria. In this webinar, I will start with an introduction to the QMDB and explain the key benefits and most important features. I will elucidate the demographics of the samples the QMDB comprises and show you how the QMDB contents were validated. I will highlight an example how the QMDB can be applied and conclude with a brief summary. Let's start with the introduction. What is the QMDB? Well, the QMDB is a metabolomics research tool that can help optimize your study design and study conduct. Have you ever wondered what is the normal concentration range for any metabolite? Every human individual is different, and the metabolome varies due to external and internal factors, so normal is very hard to define. However, researchers need quantitative metabolomics reference data to assess metabolic biomarker signatures and evaluate cohort studies. To solve this problem, we have created the QMDB, a new database providing quantitative human plasma concentration ranges of more than 600 metabolites. The QMDB combines sample metadata with quantitative reference ranges based on standardized Biocrates MXP Quant 500 kit analysis and provides insights into the metabolomic differences among ethnicities, sexes, and lifestyles. The QMDB is a great tool that allows you to test whether a control group in your own study is representative of the normal healthy population. You can also directly use concentration ranges as a reference. In intervention studies, you can investigate which treatment brings the metabolism closer to normal conditions. The minimum and maximum thresholds provided can help identify and exclude outliers or participants that did not follow the study protocol. It is also possible to use the concentration ranges for in silico studies, comparing different subgroups within the healthy population. Finally, you may apply the exported values in data science, for example as an input for pattern recognition algorithms to identify novel metabolite signatures behind certain donor attributes. A very useful feature of the QMDB is that it is possible to select your specific subpopulation of interest. The QMDB allows filtering for basic demographics like sex, age, BMI, or ethnicity. You are able to select the samples according to the fasting status or the assay used to measure them. And there are options to filter for fitness, smoking behavior, and alcohol consumption. The data originate from samples of more than 1,000 healthy human subjects of different age categories. These have been collected in several controlled epidemiological studies in collaboration with universities and scientific research institutes. Healthy in this context means that all donors underwent a medical screening and were not diagnosed with any current or chronic physiological or psychological disease. Further great features of the QMDB include the option to filter by date of upload, which means retroactive access to the database is granted at any time point. For users whose organizations contributed to the QMDB contents, there is an option to restrict to your own data, which makes it easy to compare it with the total QMDB contents. In the table displayed, you can select or sort by single metabolites or metabolite classes of interest. You can export the data as text, comma-separated file, or Excel file. The export contains a summary of the selected filters by default to clarify how the ranges were calculated. We also provide an Excel template to facilitate boxplot visualization and statistical analysis of your exports. Let's have a closer look at the demographics of the samples the QMDB comprises. Both sexes are about equally represented in the QMDB samples. The average age of the donors was 64.9 years, so slightly above the average of the general population. In the highest age category, meaning at least 90 years, it became increasingly difficult to identify participants completely free of medical conditions. It was therefore decided to allow participants that were healthy but had had surgical operations like hip replacements or herniation repairs in the past, which were completely resolved at the time of sample donation. Many study participants considered were overweight or obese. It was decided to set a threshold excluding participants from the QMDB at a body mass index of 35 or more, which is the definition of severe obesity according to the World Health Organization and is frequently used as a threshold for morbid obesity in modern medicine. The mean BMI of the QMDB sample donors was 26.5 kilograms per square meter. 65% of the QMDB sample donors were of white racial background. The ethnic origin of these was mostly Caucasian, while Hispanics or Latinos were a minority. 27% of the QMDB sample donors were Black or African American. It is planned to expand the racial origins represented in the QMDB in the future. Most of the samples currently included in the QMDB were obtained from fasted individuals, as this was a requirement according to the sample collection protocols for the studies. Venous blood samples were collected in the morning after an overnight fast. The collection procedure was consistent with guidelines for biomarker studies. Coming to the lifestyle categories, fitness was assessed with questionnaires regarding performance, frequency, or duration of various high-intensity activities. Levels of physical activity and the time spent with high-intensity activities were estimated from responses. Based on this, the participants were categorized as not active, moderately active, active, or highly active. Note that even participants in the highest category are usually not athletes. They are just more active than average. Considering the classification is based on estimates, the fitness categories should be considered an approximate labeling. Furthermore, smoking and drinking behavior of participants was included in the QMDB. Just like the physical activity, these pieces of information were self-reported, so it is possible that participants underreported their smoking behavior and alcohol consumption. Note that only 3% of the participants were current smokers, which is probably connected to the fact that smoking increases the risk for a plethora of diseases, and thus only a fraction of smokers was healthy enough to be eligible for this database. There is a natural hesitation to rely on external reference values in scientific studies because experience has shown that external controls are usually less suitable than controls obtained in the same study. This is especially true for metabolomics, because measurements obtained by different laboratories used to be incomparable historically. It was therefore necessary to assess whether the metabolite concentration ranges in the QMDB were comparable to concentration ranges of independent control groups from different studies. The QMDB contents were compared to 6 other datasets comprising plasma metabolite concentration data from healthy control cohorts. 2 datasets were measured with the MXP Quant500 kit, the other 4 with the Absolute IDQ P180 kit. The studies had diverse backgrounds and were originally focused on quality control, neurological diseases, nutrition, or were collected to identify healthy reference ranges, just like the QMDB. The datasets were compared to the QMDB using principal component analysis, assessment of sample quality based on concentrations of certain metabolites and ratios, statistical comparison of the concentration means, and an outlier analysis using Takis fences. The principal component analysis showed that the metabolomes of the QMDB cohort and other healthy datasets were mostly very similar. The 95% T2 Hoteling's confidence ellipses of the QMDB generally showed a high overlap with the control cohort, provided concentrations were normalized to the target values for Biocrates quality control samples, which is mandatory for MXP Quant500 kit data anyway. Removing lipemic and low-quality samples from the external datasets increased the overlap of the sample clouds. Using the QMDB Excel template for visualization and statistics, we generated a side-by-side comparison of metabolite concentration ranges and found the QMDB metabolite concentration ranges were quite comparable to other healthy control datasets, especially for polar metabolites. Wherever possible, metabolite concentrations and metabolite ratios known to be altered when samples were not processed in time or underwent several freeze-thaw cycles were assessed, and all the QMDB samples showed acceptable sample quality. We also employed the QMDB Excel template for visualization and statistics for a statistical comparison of means. We used 3 criteria to identify markedly different concentration ranges: a fold change of at least 1.5, a Q value lower than 0.01, and that the standard deviations should not overlap. Only between 2 and 7% of the concentration means were markedly different from the means in other datasets. In all of these comparisons, the percentage stayed below the acceptance threshold, which we set at 10%. The outlier analysis of metabolite concentration means in the different datasets revealed a couple of outliers in other control datasets, but none in the QMDB. Extreme fold changes between the datasets were also monitored. These were defined as at least threefold difference between the mean in a dataset and the mean concentration according to all datasets. The number of extreme metabolite concentrations in the QMDB was below average. Thus, all of these analyses showed that the QMDB is indeed suitable to serve as a quantitative metabolomic reference database. In this case study, we applied the QMDB as a reference for a study without healthy control group. A dataset of 69 samples from patients with inflammatory bowel disease was used, consisting of female and male patients diagnosed either with Crohn's disease or ulcerative colitis. The datasets were analyzed by statistical comparison of means using the QMDB as a control group. This showed that 97 analytes differed significantly between the IBD dataset and the QMDB, defined by a fold change of at least 1.5 and a Q value below 0.01. The significant differences were observed in polyunsaturated fatty acids, triglycerides, and microbiome-related metabolite levels, which is consistent with the scientific literature on metabolomic changes occurring in inflammatory bowel disease. The QMDB thus fulfilled its purpose as healthy reference, confirming the legitimacy of the results obtained and enabling further interpretation. With this, we come to the summary. I explained that the QMDB provides normal plasma concentration ranges of 620 metabolites for insights into the metabolomes of healthy subgroups. You can achieve greater insight without the need for additional controls, characterize your own control groups, and identify outliers, or identify novel metabolic signatures within QMDB subgroups in silico studies. I showed you the QMDB contains samples from donors with different demographics and lifestyles, so you can filter for the subpopulation of your interest. The validation results proved the metabolite concentration ranges in the QMDB are similar to other healthy control datasets measured with Biocrates technology. Comparing the mean concentrations found in the different healthy cohorts, the QMDB had the lowest number of outliers. And using the QMDB as a healthy reference added additional value to a study without healthy control in the case study presented. All that is left to say is therefore make use of the benefits of the QMDB as a new quantitative reference database in metabolomics. Contribute to the growing database derived from anonymized, non-trackable data and help create a standardized global data network together with others. For more information on the QMDB, please visit our webpage. If you have further questions, please do not hesitate to approach your local Biocrates business developer or contact us via email. Thank you for watching this webinar.